Exercise 4.3.3 says row reduce matrix A to an upper triangular matrix H and then find the determinants of A. All right, so let's see. If we can row reduce A down to an upper triangular matrix, it's easy to take the determinants of upper triangular matrices. So let's do some of that. Let's do the row reduction. So let me prefabricate the row reduction here. Well, keep my grammar going. A1 is row equivalent to H as follows. All right, let's maybe look at a couple of these. You're good at row reducing. Gee, you should have just let the software do this. But then the software is going to take matrix A as input and give this thing as output, and you ain't going to know how it got there. And that's a problem in the computation of determinants. So what we'll do, I want to interchange the first and the fourth row. So that gets us a 1 up here. Then we can use this 1 as a pivot to eliminate the things below it. Okay, that'd take row 2. We need to subtract twice row 1. We need to subtract 3 times row 1 from the third row and subtract 5 times row 1 from the fourth row, and so forth. You know the routine on that. So that'll produce this matrix down here, H. So we had to go through this by hand, so we could observe that we've got one row interchange. Row interchanges to change determinants by factors of a negative. And then we've got all this row addition stuff. And row addition doesn't change determinants. So A is row equivalent to H through a sequence of, we usually denoted it with an R equals 1 row interchange, and 1, 2, 3, 4, 5, 6 row additions. Row additions don't change determinants. Multiplications of rows by a scalar changes determinants. We didn't do any of that. Plan was to avoid that and do this only using row additions and row interchange. And you can take a matrix and get it in row echelon form, not reduced row echelon form, through a sequence of only row interchanges and row additions. The only time you need to multiply a row by a non-zero scalar is when you want the pivots to be 1. And we don't need the pivots to be 1 for this. If we did, then here would come that other stuff. Hence, the determinant of A is, we got -1 to however many row interchanges there were, call it R, -1 to the R is just 1, times the determinant of H. The determinant of H is easy because it's an upper triangular matrix. So all we have to do is take a product of the diagonal entries, 1, -1, 4, and -2 with a negative out front that came from the row interchange. That'll produce +8 times -1, -8. So the determinant of matrix A, worked according to the instructions, is simply -8. Piece of cake to take determinants of upper triangular matrices. They're the products of the diagonals. All we got to do is row reduce this with great preferential treatment for row addition. That's how you get the zeros there. All them things circled, they all became zeros in the next step, and similarly throughout. So the row addition is what introduces the zeros. Excellent. Row addition doesn't change determinants. Row interchange does, and that's necessary to move things around, maybe more often than just this one time that we needed in this one. I wrote it in red to call attention to it. But we only needed, in this case, 1 row interchange. That changes determinants, but you know how. So plan is row addition and row interchange only, upper triangular matrix, product of diagonal elements. Either that, or you go to town taking the determinant of this 4 by 4 matrix by definition, and we don't want to do that. At least it's got a couple of zeros in it. But that's way lengthier, and at this stage you're quite good at row reduction. The strategy is similar to when you were dealing with systems of equations. The strategy is row echelon form, not reduced row echelon form. From there, you can find the determinants easily by taking products of diagonal elements.